Good day, everyone. The second group will now present chapters 5, 6, and 7. My name is Michaela Arscado, and I will tackle the chapter 5 together with my partner, Miss Gia Kabading. Please listen carefully as we will now discuss the integer programming. Chapter 5 has two objectives, which are to differentiate and analyze the integer programming models and to apply Excel and QM for Windows as computer solutions for integer programming problems. There are a total of three integer programming models. First, we have the total integer programming model, in which all the decision variables are required to have integer solution values. Second is the 0-1 or 0 or 1 integer model, in which all the decision variables have integer values of 0 or 1. Finally, a mixed integer model. So from the word mix, it's just a combination of the two in which some of the decision variables against some, meaning not all of the decision variables are required to have integer solutions. To enlighten you more, let's have an example. Here we have a total integer model example in which a machine shop's owner wanted to purchase some new press machines and lathe machines to expand his business. So he wanted to have an additional profit of $100 per day for each press purchased and $150 increase of profit daily for the lathe machines. So the requirements can be seen on the image. For press machine, we have a 15 square feet floor space required for $8,000 of purchase price. And for lathe machine, we have 30 square feet floor required and purchase price of $4,000. For this problem, we have the budget of $40,000 for purchasing machines and a constraint of 200 square feet floor for the available space. And the owner wanted to figure out how many machines he needs to purchase for each type to maximize the daily increase of profit that we already mentioned earlier. So as you can notice, this problem is similar as the linear programming examples in chapters 2, 3, and 4. However, the only difference is that the decision variables are restricted to integer values for the reason of the owner cannot purchase a fraction or portion of a machine, meaning hindi pa pwedeng makabili ka ng isa't kalahating machine. The linear programming model is shown on the right side of the screen. Again, the decision variables in this model are restricted to a whole machine. So this model designates as a total integer model due to the fact that both decision variables, x sub 1 and x sub 2, can assume any integer value greater than or equal to 0. For the other examples, let me introduce to you Ms. Gia Sabadi for the discussion.
Thank you, Micah, for the introduction. So, this is the continuation of Chapter 5, Integer Programming. In this slide, I'm going to present a 0-1 integer model example. 0-1 integer model allows for the selection of an activity or item where a value of 1 indicates that the item is selected and a value of 0 indicates that it is not. In this problem, the Council wants to construct facilities that will maximize the expected daily usage by the residents of the community, subject to land and cost limitations. Sa table na to, makikita natin expected daily usage at yung pinigay na cost and land requirements. Ito yung gagamitin natin para makagawa ng model na nasa next slide. In this part, we can see the constraints given to the community, such as the 120,000 construction budget and 12 acres of land. Makita na din natin dito yung model para sa problem statement. So, maximize siya kasi nasabi na to kanina, yung objective function niya na to maximize the expected daily usage ng mga residente subjected to land and cost limitations. So, yung 300x sub 1, 90x sub 2, 400x sub 3, and so on. Ayan yung mga expected usage na nakita natin sa table kanina. And yung subject 2 naman, yung under na subject 2, ayan yung mga constraints or yung limitation. Kagaya nung 120,000 na budget, 12 acres, at yung sinabi sa problem na isang facility lang ang pagpipilian between sa swimming pool at tennis center. And dito, ang X sub 1 stands for the swimming pool, X sub 2 tennis center, X sub 3 athletic field, at X sub 4 gymnasium. In this model, the decision variables o yung mga facilities can have a solution value of either 0 of 1. Kapag yung facility ay hindi napili sa construction, yung decision variable niya ay 0. At kapag napili naman yung facility na yun, yung decision variable niya ay 1. We have different type of 0-1 model constraint. One of these is mutually exclusive constraint. It happens when either of the variables can have a value of 1 or both variables can equal 0. Kagaya nito yung problem kanina regarding the swimming pool or the tennis center. The next one is multiple choice constraint. Kapag naman pumili, or the model forces a choice between the two facilities or variables. The third one is conditional constraint. From the term conditional, it happens when the construction of one facility is conditional upon the construction of another. The last one is corequisite constraint. It is a variation of the conditional constraint wherein if one facility is constructed, the other one will also be constructed and vice versa. Dito, ginamit yung example kanina sa total integer model. Kapag sinabi ito as regular linear programming model gamit ng Excel, ang lalabas na resulta ay non-integer solution of 2.22 presses and 5.56 lattes. Because the solution value must be integer, ang gagawin natin ay i-round off natin ito sa closest integer value. Saan yung presses na 2.22 ay magiging 2 at yung lattes ay magiging 6. Makikita natin naging invisible siya dahil lumagpas siya sa constraint na 200. Therefore, in a model in which the constraints are all less than or equal to and the constraint coefficients are positive, a possible feasible solution is always ensured by rounding down. Thus, a feasible integer solution for this problem is x sub 1 equal to x sub 2 equal 5, accumulating profit of $950. However, one of the difficulties of simply rounding down non-integer value is that another integer solution may result in a higher profit. In this graphical analysis, notice that as object function edge move outward through the feasible solution space, there is an integer solution point that yields a greater profit than the rounded down solution. This solution point is x sub 1 equal 1 and x sub 2 equal 6. Makikita natin pwedeng magkaroon ng errors kapag nag-rounding down ka ng non-integer. Para makakuha ng sagot na optimal, a more direct approach for solving integer problem is required. At ito yung tinatawag na branch and bound method. It is a principle that a total set of feasible solutions can be partitioned into smaller subset of solutions. These smaller subsets can then be evaluated systematically until the best solution is found. The next topic will be discussed again by Micah.
you so much, Gia. And now we will tackling the computer solution of the integer programming problems with Excel and QM for Windows. As we can notice on the title, integer programming problems can be solved using Excel spreadsheets and QM for Windows. We will demonstrate both techniques using the examples provided previously. First, we will show to you the solution of the 0-1 integer model using Excel spreadsheet. As you can remember, the model for this problem is formulated as you can see on the screen. Exhibit 5.2 will demonstrate how would it look like applying in an Excel spreadsheet. Decision variables for the facilities can be found in the cells C12 to C15. These cells are currently empty or zero because the model has not yet been solved. Objective function will be found at cell 16, C16 and is shown on the formula bar. Then the model constraints are contained in cells G7, G8, and G9. Now, Exhibit 5.3 will show that we have established the 0-1 condition of our variables by constraining the decision variable cells to be binary. This will be done with the Exhibit 5.4 as shown in the Add Constraint window. This is the Add Constraint window. You need to choose the option for the binary and then click Add. Now, before we click Solve on the solver parameters, we need to click first on the Options tab and make sure that Ignore Integer Constraints is not activated or walang check. Now, when we click Solve, it will show us a figure in Exhibit 5.6, which already have the answer to our problem. And this is the answer. Now, let's move on solving the 0-1 integer model example using the QM for Windows. Now, when you're on the QM for Windows on the model tab, you need to choose the option for the integer and mixed integer programming, file, and then new. Now, as you can remember, we have a total of 3 constraints and then 4 variables. Three constraints are the cost or budget, the space or acres, facility, contingency. And the 4 variables are the swimming pool, tennis court, athletic field, and the gymnasium center. I need to click the OK. And then we will have this figure and we need to fill all the informations needed for this section. Now, if we are already done filling out all the values and information, we will have this one. And on Exhibit 5.7, don't forget to click this 0/1 figure so that this will be or this will identify this is a 0-1 integer model. Now, if we are done filling all the informations needed, we need to click solve, and then we will have the answer here. Now, for the X sub 1 or the swimming pool, we will construct that one. Now, we will not construct the tennis court or the X sub 2, but we will again construct the X sub 3 or the athletic field. We will not have the gymnasium center. Now, the 700 value here will be the people per day expected usage. And now for the Exhibit 5.9, let me introduce to you the setup in spreadsheet format for the solution of the total integer model using Excel. This is just the same like we've discussed on the 0-1 integer model using Excel. We have the same features here. The decision variable, the objective function, the constraints, and the variables, which are the presses and the late machine. Now, to solve and to know more about the solution for the machine shop example, let us have Ms. Gia Kabating to continue the discussion.
Thanks again, Micah. I will now demonstrate the Excel solution of a total integer programming problem for the machine shop example using the branch and bound method. Recall that this model was formulated as maximize equal 100x sub 1 plus x sub 2 subject to yung mga constraints niya where x sub 1 equal number of presses and x sub 2 equal number of lattice. Dito sa table na input na yung mga data na nabigay. Para ma-solve natin yan, naka-solve na siya. Para makuha natin tong 1 and 6, tas yung profit niya. Solver parameters yung gagamitin. Sa solver parameters, yung unang gagawin ay set objective. Kaya siya B12 kasi ito yung objective function niya. Tapos, max yung pipiliin kasi maximize yung hinihingi sa problem. Tapos yung changing variable cells, ito yung decision variables. Tapos yung constraints niya, ayan, yung integer, yung beta ng B11, kailangan integer yung lumabas. Tapos yung E5 and E7, yung constraint niya doon. Tapos i-check yung make unconstrained variables na negative. Then, select a solving method na simplex LP. Kapag pinindot natin solve dyan, ito yung lalabas na sagot. So, 1 number of presses and 6 number of lattice equal 1,000 profit. That will be all for chapter 5. Thank you for listening. The next topic or chapter will be discussed by Fritz Morau.
Thank you, Gia. Good afternoon, sir. Good afternoon, Blackmates. In this chapter, the reporters will introduce three types of linear programming model formulations: the transportation, transshipment, and assignment problems. These three are part of a larger scale class of linear programming problems termed as network flow problems. The said problems contain special mathematical characteristics that have enabled management scientists to develop very efficient and unique mathematical solution approaches. In addition, these approaches are variations of the traditional simplex solutions procedure. In this chapter, our learning objectives would be to differentiate the three special types of linear programming model formulations and to apply the computer solution for these types of linear programming model. The first model is the transportation model. Transportation model is formulated for a class of problems that has two unique characteristics. One of them is that a product is transported from several sources to a number of destinations at the minimum possible cost. The other one is each source is able to supply a fixed number of units of the product, and each destination has a fixed demand for the product. The following example demonstrates the formulation of a transportation model. A wheat is harvested in the north and stored in grain elevators in three different cities: Gapan, Palayan, and Cabanatuan. These grain elevators supply three flour mills located in Concepcion, Paniqui, and La Paz. Grain is shipped to the mills in railroad cars, and each car is capable of holding 1 ton of wheat. Each grain elevator is able to supply the following number of tons: 150 tons in Gapan, 175 tons in Palayan, and 275 tons in Cabanatuan. Each mill demands the following number of tons of wheat per month: 200 tons for Concepcion, 100 tons for Paniqui, and 300 tons for La Paz on a monthly basis. The cost of transporting 1 ton of wheat from each grain elevator to each mill differs according to the distance and rail system, and these costs are shown in the table. For example, the cost of transporting 1 ton of wheat from grain elevator at Palayan to the mill at Concepcion is $7. The given problem is to determine how many tons of wheat to transport from each grain elevator to each mill on a monthly basis to minimize the total cost of transportation. The one being presented in the slide is the diagram of different transportation routes containing supply and demand from each city. With this example, we can formulate a linear programming model that you can see on your screen, wherein the x sub I to j represents the number of tons of wheat transported from each grain elevator. The first three constraints in this linear programming model represents the supply at each elevator: Gapan, Palayan, and Cabanatuan. The last three constraints represent the demand at each mill: Concepcion, Paniki, and La Paz. One thing we'll notice in this linear programming model is that the three mills demand a total of 600 total tons, which is the exact amount that can be supplied by the three grain elevators, which is this one. This type of model in which the supply exactly equals the demand is referred to as the balanced transportation model. On the other hand, the more realistic occurrence is an unbalanced problem, wherein the supply exceeds the demand or the demand exceeds supply. In our example, if the demand at La Paz is increased from 300 tons to 350 tons, one of the demand constraints will not be met because there is not enough supply to meet the total demand. If that happens, then the supply constraints will become an inequality. So unlike the balanced transportation model, which has an equal sign because the supply exactly meets the demand, in unbalanced transportation model, you will notice that in our formula, we will encounter an inequality sign in our formula since the supply does not meet the demand or the demand does not meet the supply. Now that we are able to determine the difference between balanced and unbalanced model, let us now discuss the computer solution of a transportation problem. Transportation problem is formulated as a linear programming model. Therefore, it can be solved with Excel using the linear programming model of QM for Windows. So, for the demonstration on how to solve a transportation problem by using an Excel, let us look at this spreadsheet setup. Notice that the objective function formula for total cost is contained in cell C10 and is shown on the formula bar at the top of the spreadsheet. It is constructed as a sum product of the decision variables in between cells B5 and B7. Decision variables normally measure the quantity of the resources to be utilized, such as quantity of the goods to be manufactured, and it is denoted in our linear programming model as x sub 1a plus x sub 1b and etc. And also, you will notice that there is a cost array in cells in between K5 and cell M7. Another thing that you'll notice is the cells in between F5 and cell F7 in column F, and cells in between B9 and D9 in row 9 labeled grain sheet, which contains the constraint formulas for supply and demand. The next exhibit is the solver parameters, containing the minimize or the simpler objective function formula. The constraint formula includes all three demand constraints as well as the all three supply constraints. Take note that in accordance with the IM, you need to select the simplex.lp to invoke the linear programming solution approach. The other computer solution is with Excel QM. Before that, let us show the figure 6.2, which is the transportation network solution for wheat shipping example. This type of transportation network solution will further be explained in the chapter 7 of our report. The other computer solution is with Excel QM. QM for Windows provides mathematical analysis for operations management, quantitative methods, or management science. When the Excel QM is activated, clicking on Transportation, as shown in the exhibit present in the slide, we set the number of sources and destination to 3 and minimizes the objective. Once we are able to type in the title, we'll click OK and the spreadsheet in Exhibit 6.4 will appear. To solve the problem, we just need to click on Solver, and when Solver appears, click on Solve. Then it will already include all the decisions variables and constraints to solve problems, as shown in Exhibit 6.5. Exhibit 6.6 simply shows the input data for our wheat shipping example. Exhibit 6.7 and 6.8 simply shows the solution results in two different labels or formats. Exhibit 6.7 shows the shipments in each cell or decision variable, plus the total costs, and Exhibit 6.8 lists the individual shipments from each source to destination and their costs. And if we are going to look closely, these exhibits are exactly similar to the difference between solver parameter and the computer solution with Excel. one exhibit having the optimal solution of the problem, and the other exhibit containing the minimized or the simpler objective function formula. Most importantly, the sensitivity analysis. Once a transportation model is set up in any software formats, it is also simple to perform sensitivity analysis. Sensitivity analysis is a method for predicting the outcome of a decision if a situation turns out to be different compared to the key predictions. That would be all for the transportation model. The next models would be discussed by Mr. Richard Von Santos.
Thank you, Fritz. Good day, everyone. I am Richard Von Santos, and I'm here to discuss the last two special type of linear programming model formulation, the transshipment model and the assignment model. After discussing the transportation model by Mr. Morao, let's now move on to the next type of linear programming model formulation, which is the transshipment model. Transshipment model is an extension of the transportation model in which intermediate transshipment points are added between the sources and destinations. Examples of transshipment points are distribution centers and warehouse. To further elaborate the transshipment model, we will use the wheat shipping example from the previous discussion. For this model, wheat is now harvested at farms in Victoria and Pura before being shipped to the three grain elevators in Gapan, Palayan, and Cabanatuan, which are now considered as transshipment points. Wheat harvested at each farm weighs 300 tons, and after being shipped to the three grain elevators, it will now be shipped to the mills in Concepcion, Paniqui, and La Paz. The shipping costs from the grain elevators to the mills remain the same, but the shipping costs from the farms to the grain elevator are as follows. Next is Figure 6.3 shows the network of transshipment routes. As compared to the previous figure 6.2, Victoria and Pura were added and they are considered as the place where the wheat will came from. Next, with the transshipment problem, a linear programming model is also developed with the supply and demand constraints. The available supply constraints for the farms in Victoria and Pura can be seen on the presentation. Then, the demand constraints at the Concepcion, Paniqui, and La Paz mills are as follows. Next, we must develop constraints from the three grain elevators. In developing the constraints, we must follow the principle in assignment model that at each transshipment points, the amount of grain shipped is also be shipped out. To further explain the idea, let us use this slide as an example. Let's say the amount of grain shipped in Japan is X sub 13 plus X sub 23, and the amount shipped out is X sub 36 plus X sub 37 plus X sub 38. Therefore, using the principle mentioned, the constraint is X sub 13 plus X sub 23 is equals to X sub 36 plus X sub 37 plus X sub 38. The transshipment constraints for Palayan and Cabanatuan are also constructed similarly, as you can see in the presentation. The complete linear programming model, including the objective function, can be seen on the presentation. The objective of the wheat shipping example is to minimize the transportation cost from the grain elevators to the transshipment points and onto the flour mills. Now, let's move on to the computer solution of a transshipment model. Because the transshipment model is formulated as a linear programming model, it can be solved with either Microsoft Excel or QM for Windows. For this example, we will use the Microsoft Excel. As you can see, Exhibit 6.11 shows the spreadsheet solution. The spreadsheet is like the original spreadsheet on the regular transportation problem in Exhibit 6.1, except that there are two tables of variables. One is for shipping from the farms to the grain elevators, and one is for shipping grain from the elevators to the mills. The decision variables are in cells B6 to D7 and C13 to E15. The constraints for grain shipped from the farm in Victoria to the three grain elevators is located in cell F6, while the amount of grain shipped to Gapan from the farms is located in cell B8. Two cost arrays have been developed for the shipping costs in cells I6 to K7 and cells J13 to L15. Similar constraints are developed for the shipments from the grain elevators to the mills. Next. In Exhibit 6.12, we can see the solver in Excel is used for our wheat shipping transshipment example. Next, Figure 6.4 shows transshipment network solution for wheat shipping example. The supply and demand are equal and the demand by the flour mills were met by Victoria and Pura. After discussing the transshipment model, let's hop on to the last type of linear programming model formulation, which is the assignment model. The assignment model is a special form of a linear programming model that is like the transportation model, but the difference is that in assignment model, the supply at each source and the demand at each destination are each limited to one unit. I will give a further example to elaborate the idea in assignment model. So, the Philippine Basketball Association or PBA has 4 basketball games on a particular night. It will be held in Antipolo, Cubao, Pasay, and Pasig. The office wants to assign 4 teams of officials to the 4 games in a way that will maximize the total distance traveled by the officials. With the idea of assignment model, the supply is always one team of officials and the demand is for only one team of officials at each game also. The linear programming formulation of the assignment model is similar to the transportation model except all the supply values for each source is equal to 1 and all the demand values at each destination is equal to 1. Let's now move on to the computer solution of assignment model. The assignment problem can be solved using the assignment modules in QM for Windows and Excel QM and also with Excel spreadsheets. In the case of assignment problems, Excel can be used to solve these types of problems, but only as a linear programming models. Exhibit 6.13 shows an Excel spreadsheet for our PBA basketball official example. The objective function is in cell 11 was developed by creating a mileage array in cell C16 to F19 and multiplying it by the decision variables in cells C5 to F8. The model constraints for available teams are contained in the cell in column H, and the constraints for team officials at the game sites are contained in cells in row 10. Next, Exhibit 6.14 shows the solver parameters screen for our example. Before clicking on solve, remember to invoke simplex LP to solve as a linear programming model. Exhibit 6.15 shows another way of solving assignment problems, which is using Excel QM. Excel QM includes a spreadsheet macro, especially for assignment problems. As you can see on the presentation, the top shows the solution on the PB situation, and at the bottom is the distance in miles for each team of officials to each game location. Exhibit 6.16 also shows the solution of PBA assignment of official problem. Next, Figure 6.5 shows assignment network solution for PBA official example. One team of official provided by PBA will go on each team in Antipolo, Cubao, Pasay, and Pasig. Exhibit 6.17 and Exhibit 6.18 shows how to solve assignment problem using QM for Windows in a assignment module. Exhibit 6.17 shows the data input of the PBA example, and Exhibit 6.18 shows the solution of solving the assignment problem of the PBA. That's all for Chapter 6, and for discussion of Chapter 7, may I call on Ms. Elsa May Zoilo.
We are now down to chapter 7 entitled Network Flow Models, and this chapter is divided into 3 key points. We have network components, and the network flow models. Let us first define what is a network. It is an organization of passageways that are interconnected at several locations, through which one or more things travel from one point to another. It is a popular management science technique because, first, network is drawn as a diagram, meaning it provides a clear picture of the system. This makes it possible for an entity's manager to visually interpret and understand their overall system. The second reason is the large number of real life systems can be modeled as networks. Creating networks implies that various real life systems can be transformed into simpler and straightforward concepts. Next, we have the network components, which are nodes and the branches. Nodes represent junction points and it is usually denoted by circles, while branches, it connects the nodes and denoted by lines. For example, we have here this picture. Let us identify what are the nodes and the branches. So according to the definition earlier, nodes are represented by circles and it usually pertains to the localities. So in this figure, Atlanta is the node 1, Nashville is node 2, node 3 is Memphis, and node 4 is St. Louis. Next is the last key point, which is the network flow model. It refers to the flow of items through a system and the three types of problems that network flow analyze. We have first, shortest route, second, minimal spanning tree, and third, minimal flow. For the shortest route, it aims to find the shortest distance from the origin to its destinations. We have 5 steps to derive the shortest route as you can see on the current slide. We just need to select the shortest direct origin, establish a permanent set, and repeat the process until all nodes have joined this permanent set. For the sample problem, we have Stagecoach Shipping Company transport potatoes by 6 trucks from Los Angeles to 6 cities in the West and Midwest. The shipping company manager wants to determine the best routes in terms of minimum travel time for the trucks to take to reach their destinations. Para mas madali nating ma-imagine, I presented the system of truck routes as a network. Since sa Los Angeles ang origin or panggagalingan ng trucks, automatic yun ang node 1. Then the other nodes, pwedeng random na yung pag-assign ng numbering. Node 1 is part of the permanent set since there is no route to it. Walang papasok dahil palabas sa kanya lahat ng trucks. As seen in the figure, there are 3 branches coming from the node 1. From node 1 to 2, it will be 16 hours. From node 1 to 3, it will be 9 hours. And from node 1 to 4, it will be 35 hours. The shortest time is 9 hours. That is from node 1 to node 3. So, imamark natin yung branch na yon with a heavy line para may palatandaan tayo na yun ang ating napiling shortest route. Next, ganun ulit yung gagawin natin. Since the node 1 to 3, it now belongs to the permanent set. Ito yun. I-identify naman natin ulit yung shortest route from the node 1 to node 2, 4, and 6. So in this figure, from node 1 to 2, 16 hours, from node 1 to 4, 35 hours, or pwede ring from node 1, dadaan muna ng node 3, then node 4, that will take 24 hours in total. From node 1, dadaan ng node 3 para makapunta sa node 6. And the cumulative travel time is 31 hours. The shortest route from node 1 is going to node 2, which is 16 hours. Yung branch 1 to 2 will be denoted by a heavy line also since magiging part na siya ng permanent set. So makikita natin dito sa next slide, yung node 1, 2, and 3 is now part of permanent set. So dito sa mga branches na to, hahanapin ulit natin kung ano yung shortest route. So in this case, the branch 3 to 4, yung shortest from the node 1, which is 24 hours in total. So magiging part ulit siya ng permanent set. So the permanent set now is 1, 2, 3, and 4. And we will repeat the process until hanggang node 7 makompleto ng part sila ng permanent set. So in summary, we have route 1 to 2, 16 hours. route 1 to 3, 9 hours, and so on and so forth. Next is the computer solution of the shortest route problem with QM. Using the QM for Windows, the shortest route from any node in the network to any other node can be easily determined. The first put all of the distances between the nodes and branches as this will be the basis. So let's look at the top of the solution screen. So by indicating the desired origin and the destination nodes, we can generate the shortest route in just a few seconds. So this is the actual QM. So for example, we want to determine the shortest route from origin 1 to its destination, the node 7. We just need to click the solutions button and then at the shortest route natin. So we will start from the node 1, pupunta ng node 3, pupunta ng node 4, and then node 7. And the cumulative distance is 43 hours. To determine the shortest route, we can also use Excel spreadsheets and utilize the 0 to 1 integer linear programming discussed in the previous chapters. So we have to set up our decision variable, 0 if it is not selected as part of the shortest route, and 1 if it is selected. And in this problem, our objective function is to minimize the sum of the multiplication of each branch value and the travel time for each branch. And in setting up our constraints, we must always remember the conservation of flow, meaning whatever comes into a node must also go out. So we can observe that only the first and last integer linear equations are equal to 1, and the rest is 0. It is because that the node 1 and node 7 violates the conservation flow. This is now our Excel spreadsheet that contains our already encoded 0 to 1 linear equations na ginawa natin kanina. So as you can see, on the table, we have this row. This is our decision variables. Meaning, lalabas dito mamaya, 0 kapag it is not selected as part of the shortest route, and 1 if it is selected. And this cell naman, lalabas dito yung cumulative distance ng shortest route natin. While in here, this is our constraints. So 1 if it violates our conservation flow, and 0 if not. Para mas mapadali yung ating pagsosolve ng shortest route, we can use the Excel solver. Located in the Data tab, then click the solver. Then we have to set our objective to minimize the multiplication of the distances. And then we will put our constraints here. So 1 kapag it violates the conservation flow, and 0 kapag hindi. So you just have to click the solve. Then okay. And ayan, lumabas na kung ano yung kasama sa shortest route natin. We have the branch 1 to 3, 3 to 4, then 4 to 7. And our cumulative distance is 43 hours. So dito rin sa ating constraints, lumabas nga na the node 1 and node 7 violates the conservation flow. As you can see in my current slide, these are the 3 ways na ginawa natin para makuha yung shortest route. So nakadepende na sa inyo kung ano yung gusto nyong gamitin na way para makuha ng mabilis yung shortest route. And this is now the end of my part. The next part will be discussed by Agawili.
Thank you, Elsa. I'm here to discuss the spanning tree problem. The goal of the preceding section's shortest route problem was to find the shortest routes between the network's origin and the destination nodes. Kung makikita natin sa preceding examples na related lang sila ng shortest route problem. The minimal spanning tree problem is related to the shortest route problem in that the goal is to connect all nodes in the network while keeping overall branch lengths to a minimum. The resulting network spans connects all the network's points at a minimum total distance or length. Para mas maintindihan natin yung minimal spanning tree problem, let's consider the following example to explain the least spanning tree problem. A television cable system will be installed in a town by the Metro Cable Television Company, made up of 7 suburbs. Each suburb must be linked to the main cable system. The cable television firm wishes to lay out the main cable network in such a way that the total length of a cable that must be placed is minimized. The alternative paths available at a cable television company with town council approval and the length of cable in thousands of feet. The figure depicts the requirement for each path. So yung figure is the network of possible cable TV paths. Ito yung gagamitin natin sa problem. Here's the minimal spanning tree solution approach. The strategy to solving the minimal spanning tree problem is actually simpler than the shortest path method. We can begin at any node in the network using the minimal spanning tree solution strategy. However, the customary method is to begin with node 1. Starting at node 1, we choose the nearest node, or for example the shortest branch, to join our spanning tree. The shortest branch from node 1 to node 3 is 9 in length, 1000 feet. This figure depicts the branch with a thick line. Ito, yung 1 to 9, ay 1 to 3. We now have a spanning tree with two nodes, 1 and 3. The next step is to find the closest node that is not already in spanning tree. Node 4 with the branch length of 15,000 feet is the node closest to either node 1 or node 3. This figure depicts the insertion of node 4 to our spanning tree. Ito yung pag-insert niya. Yung thick line, ayun yung dinidepict niya, yung 3 to 4. So yung spanning tree natin ay may nodes 1, 3, and 4 na. Then we just repeat the process of selecting the node that is closest to our current spanning tree, nodes 1, 3, and 4. So node 2 is the closest node that is not yet connected to the nodes in our spanning tree. The branch runs 12,000 feet from node 4 to node 2. This figure depicts the addition of node 2 to the spanning tree. So yung figure natin ay may spanning tree na with nodes 1, 2, 3, and 4. Nodes 1, 2, 3, and 4 have been added to our spanning tree. Node 5 is the nearest to the spanning tree. This is node 5, having a branch length of 14,000 feet to node 4. As a result, as seen in this figure, node 5 joins our spanning tree. So yung spanning tree natin ay may nodes 1, 2, 3, 4, and 5 na. Here, and here. Nodes 1, 2, 3, 4, and 5 have been added to the spanning tree. Node 7 is the nearest node. This is node 7 that is not currently connected to the spanning tree. The branch connecting node 7 and 5 is 8,000 feet long. The addition of node 7 to the spanning tree is shown in this figure, 5 to 7. So yung figure natin ay may spanning tree na with nodes 1, 2, 3, 4, 5, and 7. Nodes 1, 2, 3, 4, 5, and 7 have now been added to our spanning tree. Node 6 is the only node, ito yung node 6, that is not connected to the spanning tree. Node 7 on the spanning tree is the closest to the node 6 with a branch length of 14,000 feet. This figure shows the complete spanning tree, which now includes all 7 nodes, which are 1, 2, 3, 4, 5, 6, and 7. Yung spanning tree natin, yung pinakaunang spanning tree, kailangan nagre-require lang siya ng 72,000 feet of television cable to connect the 7 suburbs, which are represented by these nodes. Starting at any of the 6 nodes other than node 1 yielded the same minimal spanning tree. This is the minimal spanning tree for the cable TV network. So ayun, sabi ko lang naman, simple lang naman yung topic na to. So in summary, select any starting node. Conventionally, node 1 is selected. Number 2, select the node closest to the initial node to join the spanning tree. Number 3, choose the nearest node that is not currently in the spanning tree. And number 4, step 3 should be repeated until all nodes have been joined the spanning tree. And for those curious, ito yung computer solution ng minimal spanning tree problem with QM for Windows. Thank you for listening. I will now pass it on to the next reporter.
Thank you, Leonard. And the last topic to be discussed is the maximal flow problem. The maximal flow problem is used to maximize the amount of flow of items from an origin to a destination. In the shortest route problem, we determine the shortest truck route from the origin, Los Angeles, to 6 destinations. In the minimal spanning tree problem, we found the shortest connected network for television cable. In neither of these problems was the capacity of a branch limited to a specific number of items. That is why we have the maximal flow problem, which maximizes the total amount of flow from an origin to a destination of a network problems in which the branches of the network have limited flow capacities. So examples of problems that involves maximal flow are water, gas, or oil through a network of pipelines, flow of forms through a paper processing system such as in a government agency, flow of traffic and flow of products through a production line system. And it can be observed that in these types of networks, there are limited flow of capacities in some of its branches. The steps of the maximal flow solution methods are as follows. So I'm just going to read it briefly, but you will appreciate its application in the following sample problem. So step 1, arbitrarily select any path in the network from origin to destination. 2, adjust the capacities at each node by subtracting the maximal flow for the path selected in step 1. 3, add the maximal flow along the path in the opposite direction at each node. And 4, repeat steps 1, 2, 3 until there are no more paths with available flow capacity. So the gist of the sample problem is that there is a railway system from Omaha to St. Louis, and the contract limits the number of railroad cars the company can secure on each branch during a week. So the company wants to know the maximum number of railroad cars containing tractor parts that can be shipped from Omaha to St. Louis during a week. Note that the number on each branch to the immediate left of each node, this one, these numbers, ayan, they are the number of cars available for shipping in the opposite direction. And tinatawag naman na directed branch ang branch na may one direction lang ang flow, katulad nitong flow from node 1 to node 2 dahil meron siyang papuntang 6 available cars, pero kapag pabalik, 0 na yung available cars. Kaya ang tawag sa branch na to is directed branch. And undirected branch, kung both directions ang flow ng branch, katulad sa node 3 to node 4 and node 4 to node 3, dahil ang papunta from node 3 to node 4, there are 2 available cars, while node 4 to node 3, there are 2 available cars then. So there are merong both direction ang flow ng branch. So now let us apply the steps of the maximal flow solution method. So for step 1, arbitrarily select any path in the network from origin to destination. So pipili lang tayo ng kahit anong path dyan as long as there are available cars papunta sa destination natin. So let's try 1, 2, 5, 6. And pwede yung 1 to 5, 6 kasi from 1 to 2, there are 6 available cars. From 2 to 5, there are 8 available cars. And from 5 to 6, there are 4 available cars. So step 2, adjust the capacities at each node by subtracting the maximal flow for the path selected in step 1. So among 4, 6, and 8, ano ang pinakamababa? Siyempre yung 4. So 4 is the maximal flow for path 1, 2, 5, 6. So ang gagawin natin, isasubtract lang natin tong 4 sa mga available cars. So 6 minus 4 is 2. 8 minus 4 is 4. 4 minus 4 is 0 na. And then, step number 3, add maximal flow along the path in the opposite direction at each node. So, i-add lang natin yung maximal flow doon sa mga opposite direction. So, from 6 to 5, merong 0. So, 0 plus 4 is 4. 5 to 2, merong 0. So, 0 plus 4 is 4. 2 to 1, merong 0. So, 0 plus 4 is 4. Step 4, repeat steps 1, 2, and 3 until there are no more paths with available flow capacity. So, ulitin lang natin yung ginawa natin kanina. Pero let's just take note na ang 1, 2, 5, 6 na path ay merong maximum of flow, meron siyang 4 flow capacity, 4 cars. So, next, try natin ang path ng 146. So, sa 146, pwede ang 146 kasi from 1 to 4, merong 4 available cars, and 4 to 6, merong 5 available cars. So, ang mas mababa sa 4 and 5 ay 4. So, 4 ang maximal flow natin. 4 minus 4 is 0, and 5 minus 4 is 1. Step 3, mag-a-add na tayo ng i-add natin yung maximal flow natin sa opposite direction. So, 6 to 4, merong 0. So, ang maximum flow natin is 4. So, 0 plus 4 is equal to 4. Ang flow natin from 4 to 1 ay 0. So, 0 plus 4 is 4. And let us also take note na ang flow natin from 1, 4, 6 ay there is a maximum of 4 cars. Try pa tayo ng iba, 136. Ang flow from 136 ay pwede dahil from 1 to 3, there are 7 available cars, and from 3 to 6, there are 6 available cars. So, ang mas mababa sa 7 and 6 ay 6. So, 6 ang maximum flow natin. 7 minus 6 is 1, and 6 minus 6 is 0. Add natin sa opposite direction. 0 plus 6 is 6. 0 plus 6 is 6. So, sa path natin na 136, meron tayong 6 maximal flow. Ano pang pwede nating path na gamitin? Let's try 1346. 1346. Ayan, gamitin natin ng ibang color. 1346. So, sa 1346, pwede kasi 1 to 3, meron pa available na 1. 3 to 4, meron pa available na 2. And 4 to 6, meron pa available na 1. So, among 1, 2, and 1, ang pinakamababa is 1. So, 1 minus 1 is 0. 2 minus 1 is 1. 1 minus 1 is 0. So, ibig sabihin, ang flow natin ng 1346 ay may maximum na 1. So, may any other path pa ba na available pwede natin gamitin? What if 1, 2, 4, 6? Ang flow from 1 to 2 ay meron pa tayong 2. 2 to 4, meron pang 4. Pero 4 to 6, meron ng 0. So, hindi na pwede. So, wala na tayong iba pang pwedeng daanan. Ito na magiging itsura niya. So, there is a maximum flow of 15 cars from Omaha to St. Louis. Para natin nakuha yung 15, balikan natin yung ninote natin. Flow from path 1256, meron tayong 4. Sa path 146, may 4. Path 136, may 6. Path 1346, may 1. So, 4 plus 4, 8 plus 6, 14 plus 1, 15. So, 15 ang maximum flow natin from Omaha to St. Louis. And for the last topic to be discussed is the computer solution of the maximal flow problem with QM for Windows. So the maximal flow problem can also be solved with Excel, just as how the shortest route problem was solved. The following steps are suggested to formulate the model. We're going to formulate it as an integer linear programming model, which is step 1, where x sub I to j is equal to the flow along branch I to j and integer. So step 2, eliminate flow along a branch in the opposite direction in order for us to lower the volume and complication of the model formulation. Example of this is the flow from 4 to 2, which is 0. To create a continual flow through the network, we will create a new branch from node 6 back to node 1 and refer to it as x sub 6 to 1. And that's for step number 3, which is to create a new branch from node 6 back to node 1, which is x sub 6 to 1. The objective is to make a flow network where most that goes through and comes out at node 6 is the most that can go through the network beginning at node 1. Therefore, we maximize the size that flows from node 6 to node 1, resulting to step number 4, maximize z is equal to x sub 6 to 1. Remember that the limitations or constraints is just the same as the premise of the shortest route problem, wherein whatever flows into a node must flow out. Therefore, in node 1, values flowing from 6 to 1 must flow out through branches 1 to 2, 1 to 3, 1 to 4 consequently. So x sub 6 to 1 is equal to x sub 1 to 2 plus x sub 1 to 3 plus x sub 1 to 4, which can be derived to x sub 6 to 1 minus x sub 1 to 2 minus x sub 1 to 3 minus x sub 1 to 4 is equal to 0. Likewise, limitations on node 2 can be derived as x sub 1 to 2 minus x sub 2 to 4 minus x sub 2 to 5 is equal to 0. And for the last step, we must also develop a set of constraints reflecting the capacities along each branch. So I don't think I need to read all of this, but this figure at the right side is how it's gonna be after the constraint for the branch capacities are obtained. So after the formulation has been done, using your Excel QM, click on the maximal flow on the ribbon and enter the desirable information like this, and click solve. And this will be the result, this one. So there is a maximal network flow of 15 cars. And that is all for the second group's report from chapter 5 to 7.